There is no single thing called a black hole. There are at least 8 fundamentally different types, each formed through completely different processes, each behaving according to different physics, each sitting at a different point on a scale of mass so extreme that the human mind was not built to hold it. At one end of that scale, a primordial black hole smaller than an atom, a relic from the first fraction of a second after the Big Bang. So small it may be passing through your body right now, leaving no trace, detectable by nothing we have yet built. At the other end, Phoenix A, a black hole containing 100 billion times the mass of our Sun. So massive that its event horizon is larger than our entire solar system, and so dense in terms of gravitational influence, and yet so counterintuitively diffuse at its boundary that a person falling through its event horizon would feel nothing unusual, would not even know they had crossed the point of no return for days. Between these two extremes lies a spectrum of objects so varied in their properties, their origins, their behaviors, and their implications for the laws of physics that calling them all by the same name, black hole, is a little like calling a match and a nuclear reactor both fire. The word is technically correct in both cases, but it conceals almost everything that matters. Tonight, this documentary covers all 8 types. We will begin with the most common, the stellar black hole, formed from the collapse of a dying star, and work outward through intermediate black holes, the long-suspected missing link that science only confirmed in 2024. We will visit the supermassive monsters at the centers of galaxies, including our own, and the ultramassive objects so large they strain the vocabulary of astrophysics. We will go into the physics of rotation, because a spinning black hole is not just a faster version of a still one. It is a fundamentally different object with regions of spacetime that no complete theory of physics yet describes. We will follow the rogue black holes, the ones that have been kicked out of their galaxies and are now racing through the universe at millions of kilometers per hour, invisible, traceable only by the destruction they leave behind. And we will end at the theoretical frontier, with micro black holes, objects so small that quantum mechanics becomes dominant, objects that Stephen Hawking predicted would slowly evaporate and eventually vanish in a final burst of energy. Objects that have never been directly observed, but whose existence is supported by some of the most elegant mathematics in physics. Stay until Chapter 6. Because in 2025, the James Webb Space Telescope confirmed that a runaway supermassive black hole is currently racing through space at 2.2 million miles per hour, leaving a trail of newly formed stars 200,000 light-years long behind it. And scientists are still tracking where it is going. Or if this kind of science is what you come here for, if understanding the universe at its most extreme is something that matters to you, please consider subscribing. This channel exists to take the most difficult and most extraordinary ideas in science and give them the time and depth they deserve. And the black hole, in all 8 of its forms, is one of the most difficult and most extraordinary ideas science has ever produced. Now, let us begin. Every second, somewhere in the universe, a massive star is running out of fuel, not slowly, not gracefully. In the final moments of a star's life, the process that has sustained it for millions or billions of years suddenly stops. And what follows happens in fractions of a second. A star lives by burning, not burning in the chemical sense, not the combustion of wood or fuel, but nuclear fusion. In the core of every star, hydrogen nuclei are being slammed together under conditions of pressure and temperature so extreme that they merge, forming helium, and releasing energy in the process. That energy pushes outward against the weight of the star, pressing inward. The star exists in a permanent balance between these two forces: gravity pulling in, fusion pushing out. When the fuel runs out, that balance ends. The outward pressure vanishes, and gravity, which has been held at bay for the entire life of the star, wins instantly. The core collapses inward at roughly a quarter of the speed of light. In less than a second, a core that was once the size of Earth is compressed to a sphere roughly 10 to 20 kilometers across. What happens next depends entirely on one number: mass. If the collapsing core has a mass between about 1.5 and 3 solar masses, the collapse is halted by a quantum mechanical effect called neutron degeneracy pressure. The result is a neutron star, an extraordinarily dense but stable object, the collapsed core preserved as a city-sized ball of neutrons. But if the core is heavier than roughly 3 times the mass of our Sun, neutron degeneracy pressure is not sufficient. Nothing stops the collapse. The core continues past the neutron star stage and reaches a density so extreme that it curves space-time completely back on itself. An event horizon forms. The escape velocity at that boundary equals the speed of light. A stellar black hole is born. This is not a rare event in cosmic terms. Stars massive enough to end this way, those with initial masses above roughly 8 to 10 times our Sun, are scattered throughout every galaxy. In the Milky Way alone, estimates suggest that somewhere between 100 million and 1 billion stellar black holes currently exist. Most of them are invisible. Without nearby material to interact with, a stellar black hole produces no light, no radiation detectable at distance, no signal of any kind. It simply exists, a region of space-time from which nothing emerges, orbiting the galactic center alongside billions of other stars, completely undetected. The ones we have found were discovered almost entirely by accident. The first confirmed stellar black hole, Cygnus X1, was identified in 1971 not by seeing the black hole itself, but by observing its effect on a companion star. The Cygnus X1 is part of a binary system, a stellar black hole and a blue supergiant star locked in mutual orbit. The black hole pulls material from the surface of its companion into an accretion disk, a swirling ring of superheated gas spiraling inward. As that material compresses and heats to millions of degrees, it emits X-rays. And those X-rays cross the 3,500 light-years between Cygnus X1 and Earth and are detectable by space-based X-ray telescopes. This is how most stellar black holes have been found. Not directly, but through the electromagnetic signatures of the violence they inflict on nearby material. The technical term is X-ray binary, a black hole and a companion star exchanging mass and emitting X-rays in the process. Approximately 50 confirmed or strongly suspected stellar black holes have been found in the Milky Way this way, which means we have found roughly 1 in 2 million of the estimated total. The rest are out there in the dark. And in 2022, astronomers found one of them without relying on X-rays at all. The European Space Agency's Gaia spacecraft, a mission designed to map the positions and motions of over 1 billion stars with extraordinary precision, noticed something unusual about a star in the constellation Ophiuchus. The star was wobbling, not randomly, but in a way entirely consistent with it orbiting an invisible companion every 185 days. When the mass of the invisible companion was calculated from the orbital dynamics, it came to 9.62 solar masses. Too massive for a neutron star, but too invisible for a live star. The only remaining explanation was a black hole. The object, designated Gaia BH1, sits just 1,560 light-years from Earth. That makes it the closest known stellar black hole to our planet by a significant margin. It is also completely dormant. No accretion disk, no X-ray emission, no visible interaction with its companion. It is simply orbiting in silence, detectable only because Gaia was watching the star it orbits with sufficient precision to notice the gravitational wobble. The discovery was followed in 2024 by an even more significant find. Gaia BH3, a stellar black hole of 33 solar masses, discovered in archival data from the same mission. The 33 solar masses makes it the most massive stellar origin black hole ever found in the Milky Way, more than 3 times the mass of most stellar black holes previously detected. And like BH1, it is dormant, invisible, except for the gravitational influence it exerts on its companion. These two discoveries change the conversation about stellar black holes in a fundamental way. The 100 million estimated to exist in the Milky Way are not all violent, X-ray emitting objects actively tearing material from companion stars. Many, possibly most, are dormant, invisible, orbiting quietly. The Gaia mission is finding them not because they are active, but because their gravity cannot be hidden. So stellar black holes range in mass from approximately 3 solar masses at the lower end, the boundary where neutron degeneracy pressure fails, to somewhere around 100 solar masses at the upper end for black holes formed from single stellar collapse. Above a certain mass, the explosion dynamics during supernova become complex enough that the star may collapse directly without a visible supernova, or may fall back into itself, producing a black hole with a mass that depends sensitively on the star's composition, rotation, and the specifics of the explosion. There is a feature in the mass distribution of stellar black holes called the mass gap, a range between roughly 3 and 5 solar masses where very few confirmed black holes exist. The upper end of the neutron star mass range and the lower end of the black hole mass range appear to be separated by a gap that is not yet fully explained. Whether this gap is a real physical feature, reflecting the physics of the explosion itself, or an observational artifact, reflecting the difficulty of detecting low-mass black holes, is an active area of research. In 2025, that upper mass limit was challenged in a spectacular way. Gravitational wave detectors, LIGO and Virgo, detected a merger between 2 black holes, each exceeding 100 solar masses. The resulting black hole had a mass of approximately 225 solar masses. So this is deeply puzzling because stellar evolution models suggest that stars in a certain mass range should undergo a process called pair instability supernova, an explosion so complete it leaves no remnant at all, meaning the black holes that merged to produce this signal should not have been able to form from single stellar collapse. The most likely explanation is hierarchical merging, previous black hole mergers that built these objects up through successive collisions, but the exact formation pathway remains uncertain. What is certain is that the mass range of stellar black holes is larger and stranger than the models predicted. What happens if you fall into a stellar black hole is worth understanding, both because it is extraordinary physics and because it illustrates why these objects are in a different category from the supermassive type we discuss next. The tidal forces near a stellar black hole of 10 solar masses, the gravitational difference between one side of a human body and the other, become significant far outside the event horizon. At a distance of roughly 1,000 kilometers, still far from the event horizon, the difference in gravitational pull between your head and your feet would exceed 1,000,000 times Earth's gravitational acceleration. This process, the stretching and eventual compression of matter into long, thin streams, is called spaghettification. Cyan infalling observer would be stretched vertically and compressed horizontally long before reaching the event horizon. This is in stark contrast to what happens near a supermassive black hole, where the event horizon is so large that tidal forces at the boundary are negligible. The stellar black hole is intimate with its violence. It kills on approach. And yet, in its dormant state, the most common form of the most extreme object in the universe sits completely invisible in the dark of the Milky Way, detected by nothing, affecting nothing except the faint gravitational wobble it induces in the star it orbits. 100 million of them, most undetected, waiting to be found by missions like Gaia as they map the motions of the stars with increasing precision over the coming decades. The stellar black hole is the foundation, the smallest, most common, most fundamental version of this class of object. Everything that follows, intermediate, supermassive, ultramassive, is built from the same basic mechanism pushed to scales that require entirely different language to describe. And the next step up that scale, the intermediate black hole, is the type that was theoretically predicted for decades and that only received proper confirmation in 2024. That story, the story of the missing link, is next. For most of the 20th century, the universe appeared to contain black holes in two distinct sizes. Small ones, the stellar remnants just described, ranging from a few to perhaps 100 solar masses, and enormous ones, the supermassive objects at the centers of galaxies, ranging from hundreds of thousands to billions of solar masses. Between these two categories, a gap, not a small gap, a gap spanning roughly 3 orders of magnitude, from a few hundred solar masses to a few 100,000, a mass range in which no black hole had been convincingly confirmed, despite decades of searching. This gap was not expected. If black holes form from stellar collapse at one end and grow to supermassive scales through accretion and mergers at the other, there should logically be objects in the transition zone. Black holes in the process of growing. Black holes that have merged a few times but not yet accumulated the fuel to grow into galactic monsters. Black holes that formed through mechanisms different from single stellar collapse. They were predicted to exist. They were simply not being found. And their absence was increasingly uncomfortable, because it suggested either that the formation pathway from stellar to supermassive was far more discontinuous than expected, or that intermediate black holes existed but were hiding in places and states that made them invisible to the detection methods astronomers were using. The search for intermediate mass black holes, defined as objects with masses between roughly 100 and 100,000 solar masses, became one of the persistent challenges of early 21st century astrophysics. The problem was method. But stellar black holes are found through X-ray binaries. They announce themselves by feeding violently on companion stars. Supermassive black holes are found at the centers of galaxies. Their influence on surrounding stars and gas is observable across enormous distances. But intermediate black holes, if they exist in the mass range between these two, might not be actively feeding, might not be at a galaxy center, might exist in globular clusters or dwarf galaxies or in the outskirts of larger galaxies, locations where the detection signatures are subtler and the background noise is higher. Several candidates were identified over the years. The strongest was HLX1, an X-ray source discovered in 2009 in the galaxy ESO 243-49. Its X-ray luminosity was too high to be explained by any stellar black hole, and its variability patterns were consistent with a black hole of roughly 20,000 solar masses. It became the best-studied intermediate black hole candidate, but it remained a candidate rather than a confirmation. Then 2024 changed everything. In the first confirmed discovery of the year, astronomers analyzing data from the Hubble Space Telescope identified an intermediate mass black hole inside Omega Centauri, the largest and most massive globular cluster in the Milky Way. Omega Centauri is an extraordinary object. It contains roughly 10 million stars packed into a sphere about 150 light-years across. It orbits the Milky Way as a satellite, but is unusual enough in its size, composition, and stellar population that many astronomers believe it is not a true globular cluster at all, but rather the stripped core of a dwarf galaxy that was consumed by the Milky Way billions of years ago. The evidence for the black hole came from the motion of stars near Omega Centauri's center. The stars were moving faster than the visible mass of the cluster could explain. Something additional, something compact and invisible, was pulling them. The mass required to account for the observed stellar velocities was approximately 8,200 solar masses. Not stellar, not supermassive, intermediate. The second confirmation came from a different direction. When astronomers studying the environment around Sagittarius A star, the supermassive black hole at the center of the Milky Way, identified another intermediate mass black hole lurking in the same region. This one had a mass estimated at several thousand solar masses, and was notable for being essentially frozen in its growth. It existed near enough to Sagittarius A star to be in a region where available gas and dust, the food supply a black hole needs to grow, had already been consumed or scattered by the larger object. The intermediate black hole was starving, surrounded by a region swept clean by its enormously more massive neighbor. These two discoveries in a single year, after decades of candidates and near misses, established beyond reasonable doubt that intermediate mass black holes are real. In May of 2025, a series of coordinated studies published across multiple journals provided the most comprehensive picture yet of intermediate black hole origins and characteristics. The studies combined data from X-ray telescopes, gravitational wave detectors, and optical observations to build a statistical picture of how these objects form and where they are likely to be found. 3 formation pathways now have meaningful observational support. The first is runaway stellar merging in dense star clusters. In the crowded cores of globular clusters, where stars are packed tightly enough that collisions and close encounters are frequent, the most massive stars can undergo a cascade of mergers before they have finished their own nuclear burning. A star that absorbs several companions in rapid succession can reach a mass hundreds of times that of the Sun before collapsing, forming a black hole in the intermediate mass range directly. The second pathway is hierarchical black hole merging. 2 stellar black holes merge, producing a more massive black hole. That object merges with another stellar black hole, producing something more massive still. Repeat this process enough times, in an environment dense enough with black holes to make such mergers frequent, and you can build an intermediate black hole from the ground up. The third pathway, less certain but increasingly supported by JWST observations of the early universe, is direct collapse. In certain conditions in the early universe, particularly in environments of very low metallicity where gas could not cool efficiently, a massive cloud of gas might collapse directly into a black hole without passing through the intermediate stage of forming stars first. Direct collapse black holes might have masses of 10,000 to 100,000 solar masses, placing them at the upper end of the intermediate range or potentially bridging into the supermassive category. The significance of intermediate black holes extends beyond simply filling a gap in the mass distribution. They may be the seeds of supermassive black holes. the supermassive black holes that exist today, some of them containing billions of solar masses, had to grow from something. In the very early universe, less than 1 billion years after the Big Bang, the James Webb Space Telescope has been finding supermassive black holes that should not yet have had time to grow as large as they are through normal accretion alone. Something must have provided a head start. Something must have already been massive when the universe was young. Intermediate black holes, formed through direct collapse or rapid stellar merging in the first generation of dense star clusters, may be those seeds. The massive starting points from which supermassive black holes grew through billions of years of accretion and merging. If this is correct, then the intermediate black hole is not merely a transitional object. It is the ancestor, the origin point from which every supermassive black hole in the observable universe descended. The implications for understanding galaxy formation are profound. If supermassive black holes require intermediate black hole seeds, and those seeds form in dense star clusters, then the first star clusters and the first supermassive black holes are not independent phenomena, but part of the same connected process of structure formation in the early universe. Gravitational wave detectors have begun to probe this territory. LIGO and Virgo have detected mergers of black holes in the upper stellar mass range, objects of 50 to 100 solar masses that represent the transition zone between stellar and intermediate. Planned future detectors, particularly the space-based LISA mission scheduled for launch in the 2030s, will be sensitive to the gravitational waves produced by mergers of black holes in the intermediate and lower supermassive mass range. These detections will not just confirm that intermediate black holes exist. They will map their distribution, measure their merger rates, and reveal whether they are common enough to be the seeds that supermassive black holes required. What we know with confidence now, after 2024, is that the gap between stellar and supermassive is not truly empty. It contains objects. Real objects. Black holes that formed through processes distinct from simple stellar collapse, through mergers, through dense environments, through the particular violence of the early universe's most extreme star-forming regions. The missing link is found. But finding it has immediately raised the next question. Because if intermediate black holes are the seeds of supermassive ones, if they grow by accretion and merging into the objects that dominate galaxy centers, then understanding the supermassive black hole requires understanding what it grew from and what environment allowed it to grow so large. And the supermassive black hole, the type that anchors every large galaxy in the universe, is the subject of the next chapter. At the center of the Milky Way, 26,000 light-years from Earth, there is a black hole containing 4 million times the mass of our Sun. It is called Sagittarius A star. It sits in a region of the galaxy so dense with stars and gas and magnetic fields that observing it directly required decades of technological development. Infrared telescopes, radio telescopes, X-ray observatories, all of them working across decades to pierce the dust and gas that separates us from the galactic center. And in 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a glowing ring of superheated plasma, the emission from material orbiting just outside the event horizon, surrounding a dark central shadow. The shadow of the event horizon itself, the silhouette of the point from which nothing escapes. This was not the first black hole ever imaged. So 3 years earlier, in 2019, the same collaboration had released an image of a black hole 6.5 billion times the mass of the Sun in the galaxy, M87, 55 million light-years away. But Sagittarius A star is ours. It sits in our own galaxy. And its image, the first photograph in human history of the black hole at the center of the Milky Way, represented something that is difficult to reduce to scientific terminology. We had looked to the center of our own galaxy and seen what is there. Supermassive black holes are defined by mass, ranging from roughly 100,000 solar masses at the lower boundary up to tens of billions at the higher end, and by location. Almost every large galaxy in the observable universe has one at its center. Not most. Almost everyone. The Milky Way, Andromeda. Every large elliptical galaxy. Every large spiral. The supermassive black hole is not a rare feature of certain galaxies. It appears to be a universal feature of galaxies above a certain mass. This is one of the deepest puzzles in modern astrophysics. Why should every large galaxy have a supermassive black hole at its center? What is the relationship between the galaxy and the black hole? Did the black hole form first and the galaxy grow around it? Did the galaxy form first and the black hole grow within it? Or did they co-evolve, growing together in a process of mutual feedback that shaped both simultaneously? The evidence increasingly supports coevolution. There is a precise mathematical relationship, called the M-sigma relation, between the mass of a galaxy's central supermassive black hole and the velocity dispersion of the stars in the galaxy's central bulge. Velocity dispersion is a measure of how fast the stars in a region are moving relative to each other, and it reflects the total mass of the system. The relationship between black hole mass and stellar velocity dispersion is remarkably tight across galaxies spanning enormous ranges of size and type. This tight correlation is not what you would expect if the black hole and the galaxy formed independently and simply happened to end up in the same place. It suggests that the growth of the black hole and the growth of the stellar population around it are regulated by the same processes, that there is feedback between them. Yes, when a supermassive black hole is actively feeding, when it is drawing in large quantities of gas and radiating enormous energy, it produces outflows. Jets and winds of high-energy material that stream outward from the vicinity of the black hole and inject energy into the surrounding galaxy. This energy can heat and disperse the gas that would otherwise form new stars, effectively throttling star formation across the entire galaxy. A black hole at the center of a galaxy can therefore regulate its own growth and the growth of its host galaxy simultaneously. As it grows, it produces more energetic outflows. Those outflows heat the surrounding gas. The heating reduces the supply of gas available for both star formation and black hole accretion. Both processes slow down. A kind of equilibrium emerges. In this feedback loop, black hole growth regulating galaxy growth is now central to models of galaxy formation and evolution. The supermassive black hole is not merely a passenger in a galaxy. It is an active participant in shaping the galaxy's history. Sagittarius A star is currently in an unusually quiet phase of this cycle. It is not actively feeding at a high rate. Astronomers describe its accretion rate, the rate at which it is consuming surrounding material, as the equivalent of a human eating 1 grain of rice every million years. By the standards of active galactic nuclei, it is essentially dormant. But dormant is not the same as still. In March of 2025, astronomers using the Atacama Large Millimeter Array, ALMA, discovered something unexpected around Sagittarius A star. The area immediately surrounding the black hole, and previously assumed to be relatively calm, was found to contain structures of rapidly moving magnetized plasma, organized into patterns that the discovery team described informally as space tornadoes. These slim, magnetized filaments, extending from the immediate vicinity of the event horizon outward, represent a form of material circulation at the galactic center that had not previously been observed. They may be connected to the mechanisms by which Sagittarius A star periodically produces brief flares of infrared and X-ray emission, flares that were detected repeatedly by the Event Horizon Telescope and by the Keck Observatory over the years preceding this discovery. The quiet black hole at the center of our galaxy is not entirely quiet. Now consider the opposite extreme. It is in February of 2024, astronomers announced the discovery of the brightest quasar ever observed, J0529-435 Xanortheres 1, a supermassive black hole 12 billion light-years from Earth, emitting so much energy that it was visible to astronomers despite being at a distance that places its light travel time at near the age of the universe. Its mass is estimated at between 17 billion and 19 billion solar masses. Its luminosity, the rate at which it emits energy, is equivalent to 500 trillion suns. To maintain that luminosity, it is consuming material at a rate of roughly 1 solar mass per day. Every 24 hours, this black hole swallows an amount of gas equal to the entire mass of our Sun. This is a quasar, an active galactic nucleus in its most extreme form, a supermassive black hole feeding so voraciously that the infalling material heats to temperatures of millions of degrees and radiates across the electromagnetic spectrum with a power that outshines the combined light of the hundreds of billions of stars in its host galaxy. Quasars were discovered in the 1960s. For decades, their extreme brightness confused astronomers who assumed they were relatively nearby objects. The discovery that they were in fact enormously distant, that their apparent brightness reflected not closeness but almost incomprehensible luminosity, was one of the most surprising results in the history of observational astronomy. We now understand quasars as the early universe's most actively feeding supermassive black holes, objects that grew rapidly during the first few billion years of cosmic history when gas was abundant and the conditions for extreme accretion were widespread. The universe we observe today is quieter than it was. Most supermassive black holes, including Sagittarius A star, are in a low-activity state. The gas supply that fed the quasar era has been largely consumed or dispersed by billions of years of stellar feedback and black hole outflows. The monsters at galaxy centers are still there. They did not disappear when their fuel supply diminished, but they are no longer feeding at quasar rates. Then in 2025, JWST delivered one of its most profound results in black hole science. A black hole designated CAPERS-LRD-Z9, observed in a galaxy existing just 500 million years after the Big Bang, was confirmed as the oldest black hole yet discovered, 13 billion years old. Formed within the first 5% of the universe's current age, and it was already supermassive at the time of observation. This is the problem that has preoccupied cosmologists since JWST began returning data. Supermassive black holes of hundreds of millions to billions of solar masses should take billions of years to grow from stellar seeds, even with continuous maximum rate accretion. Yet JWST keeps finding them fully formed in the infant universe, at epochs so early that normal growth models cannot account for their mass. Something is missing from the standard picture of how supermassive black holes form. The leading candidates for what is missing are primordial seeds, black holes that formed at extraordinary mass directly from the collapse of gas in the early universe, or rapid super-Eddington accretion in the early universe. Accretion rates that exceed the theoretical maximum that radiation pressure should allow, or a combination of both. We will examine primordial black holes in detail in the next chapter. But the observation that connects all of this, that ties the supermassive black hole, the quasar, the M-sigma relation, the space tornadoes, and the JWST mystery together, is this. The supermassive black hole is not a passive consequence of galaxy formation. It is an active participant. It grew as the universe grew. It fed when feeding was possible. It regulated the galaxies around it through energetic feedback. It is sitting, right now, at the center of essentially every large galaxy in the observable universe. Most of them quiet, most of them waiting for the next episode of accretion. All of them still shaping the structure of the universe around them through their gravity and their occasional eruptions. And yet, as extraordinary as the supermassive black hole is, there is a type that dwarfs it. Objects so massive they exist in a different vocabulary of scale entirely, for which even the word supermassive is inadequate. Those objects, and the question of how they possibly formed, are next. The universe is approximately 13.8 billion years old. The first stars did not form until roughly 100 to 200 million years after the Big Bang. The first stellar black holes, the products of the first dying stars, did not exist until those first stars had lived their lives and collapsed. That took somewhere between a few million and a few 100 million years after the stars themselves formed. Which means that for the first few 100 million years of the universe's existence, there were no stellar black holes. But there may have been black holes of a completely different kind. Primordial black holes, if they exist, formed not from the collapse of stars, but from the collapse of matter directly in the extreme conditions of the very early universe, or in the first fractions of a second after the Big Bang, when the universe was unimaginably dense and hot and pervaded by density fluctuations. Regions that were even slightly more dense than their surroundings could have collapsed under their own gravity before the expansion of the universe had time to smooth them out. The result would be black holes formed directly from the primordial plasma. No star required, no stellar evolution, no supernova, no waiting. Just the raw violence of the early universe's density fluctuations, producing gravitational collapse across a range of scales that could yield black holes with masses spanning more than 40 orders of magnitude, from objects lighter than a small asteroid to objects heavier than the Sun, depending on the size of the density fluctuations and the moment in cosmic history when they collapsed. The physics is straightforward in principle. If a region of the early universe is dense enough that the escape velocity within it exceeds the speed of light, it forms a black hole. The Schwarzschild radius for any mass can be calculated. In the extreme density of the early universe, many masses could satisfy this criterion simultaneously. The challenge is not the physics of formation. The challenge is detection. Primordial black holes have never been directly observed. Every search conducted so far has returned either null results or limits. Constraints on what fraction of the universe's dark matter could be composed of primordial black holes without violating some other observation. And those constraints are tight for many mass ranges. The smallest primordial black holes, those with masses below roughly 10,000 billion kilograms, which is about the mass of a small mountain, would have already evaporated through a quantum process called Hawking radiation. They formed. They radiated energy slowly at first, and then increasingly rapidly, and they are gone. The universe is old enough that any primordial black hole below this mass threshold has had time to completely evaporate. At slightly higher masses, those in the range of 1,000,000 billion kilograms, primordial black holes would be evaporating right now in the current epoch of the universe. If they exist in sufficient numbers, Their final evaporation events should produce gamma-ray bursts at characteristic energies. Searches for these gamma-ray signatures have placed constraints on the abundance of primordial black holes in this mass range, but have not definitively excluded them. At higher masses still, above roughly 10 to the power of 15 grams, primordial black holes would be effectively stable on cosmic timescales, too massive to have evaporated significantly in 13 billion years. These objects, if they formed in the early universe, are still here. And here is where the story connects to one of the deepest unsolved problems in cosmology: what dark matter. Dark matter, the invisible, non-luminous substance that accounts for roughly 27% of the universe's total energy content, has been inferred from gravitational effects since the 1930s. It affects the rotation curves of galaxies. It shapes the large-scale structure of the universe. It was essential to the formation of the first galaxies after the Big Bang. But what it is, what particle or object constitutes it, remains unknown. Primordial black holes in the mass range above roughly 10 to the power of 15 grams would behave exactly like dark matter. They would be massive. They would interact gravitationally, but not electromagnetically. They would not emit light in any conventional sense. They would cluster in galaxy halos. They would affect galaxy rotation curves precisely as dark matter does. If primordial black holes in the right mass range exist in sufficient abundance, they could be dark matter. Not a substitute for dark matter as a concept, but an explanation for what dark matter actually is. The mass range that remains most open, most unconstrained by current observations, is what astronomers call the asteroid mass window. Primordial black holes with masses between roughly 10 to the power of 17 grams and 10 to the power of 23 grams, corresponding to masses between that of a small asteroid and a dwarf planet, have not been excluded by any current observation. If primordial black holes exist in this range in sufficient numbers, they could account for all of the universe's dark matter without contradicting anything we have observed. This would mean that dark matter is not an exotic particle yet to be discovered. It is black holes, formed in the first second after the Big Bang, distributed throughout every galaxy in the universe, potentially passing through our solar system, through Earth, through our bodies, right now. Their gravitational interaction so weak at the scale of individual events that they leave no detectable trace. The detection strategies are improving rapidly. Gravitational microlensing, the temporary brightening of a background star when a compact, massive object passes in front of it along our line of sight, can detect primordial black holes in certain mass ranges. The macho surveys of the 1990s and 2000s ruled out primordial black holes of certain masses as the sole component of dark matter. But the asteroid mass window remains open. Were the connection to the early universe problem, the JWST puzzle of supermassive black holes existing too early, provides another window. If the seeds of supermassive black holes were not stellar but primordial, if the massive black holes that anchored the first galaxies were not the products of stellar evolution, but of direct cosmological collapse, then understanding primordial black holes is not an academic exercise. It is essential to understanding how every large structure in the universe came to exist. In 2024, new theoretical work proposed that primordial black holes in the range of thousands to millions of solar masses, formed through direct collapse in the early universe, could have provided exactly the seeds that JWST is seeing. Black holes already massive at the time of the first galaxy formation. Black holes that did not need to spend billions of years accreting to reach supermassive scales, because they were born massive. In 2025, The connection deepened further when researchers proposed that supermassive black holes could act as natural particle colliders, their extreme gravitational fields providing energies comparable to human-built accelerators, potentially producing signatures that could help identify dark matter particles if dark matter is a particle rather than a black hole. The primordial black hole sits at the intersection of three of the deepest unsolved problems in physics. What is dark matter? How did supermassive black holes form so early? What happened in the first second after the Big Bang? Now, none of these questions can be fully answered without knowing whether primordial black holes exist, and in what masses and abundances. They may be the most important type of black hole we have not yet confirmed, and they connect directly to the next type. Because primordial black holes, like all black holes, can rotate. And a rotating black hole is not simply a spinning version of a static one. It is an object with a fundamentally different geometry of spacetime around it, with regions that have no analog anywhere else in the known universe. That type, the Kerr black hole, is the subject of the next chapter. In 1963, a New Zealand mathematician named Roy Kerr solved a problem that had been open for nearly half a century. Einstein published his theory of general relativity in 1915, but the equations of general relativity describe how mass and energy curve spacetime, and how the curvature of spacetime determines how matter and light move. They are among the most elegant and powerful equations in physics. Finding exact solutions to those equations, mathematical descriptions of specific physical situations, is an extremely difficult problem. The first exact solution was found by Carl Schwarzschild in 1916, just months after Einstein published the general theory, while Schwarzschild was serving in the German army on the Eastern Front. His solution described the spacetime geometry around a perfectly spherical, non-rotating, uncharged mass, a static black hole. For 47 years, this was the only exact black hole solution available, and it was almost certainly unphysical in an important sense, as nothing in the universe is perfectly still. Everything rotates. Stars rotate, because the gas clouds they formed from had angular momentum, and that angular momentum is conserved as the cloud collapses. Black holes formed from collapsing stars inherit their progenitor's rotation. Supermassive black holes grow by accreting material from accretion disks that impart angular momentum to the black hole as material spirals in. A black hole that is not rotating, a Schwarzschild black hole, is an idealization, a mathematical simplification, useful for understanding certain properties of black holes, but not a realistic description of any black hole that actually exists. What physicists needed was a solution that described a rotating black hole. Kerr found it in 1963. And what the Kerr solution revealed about the geometry of spacetime around a rotating black hole was so strange that it took years for the full implications to be absorbed. The first difference between a Schwarzschild and a Kerr black hole is visible at a distance. A non-rotating black hole sits at rest relative to the distant universe. Spacetime around it is curved, but it is curved symmetrically in all directions. The black hole does not impose any preferred direction on the space surrounding it. A rotating black hole is different. It spins, and as it spins, it drags spacetime with it. The fabric of space itself, in the region around the black hole, is being swept around in the direction of the black hole's rotation. This effect is called frame dragging, or the lens-thirring effect, and it means that any object near a rotating black hole, even one attempting to remain stationary with respect to the distant stars, is being dragged around by the rotating spacetime whether it wants to be or not. The region within which frame dragging makes stationary motion impossible is called the ergosphere. The ergosphere is outside the event horizon. It is a region of space you could enter and exit. But within the ergosphere, the rotation of spacetime is so extreme that you cannot remain stationary relative to the distant universe. You are being carried along by the rotating spacetime, regardless of any thrust or propulsion you apply against it. The ergosphere has a practical consequence that has fascinated physicists since Penrose described it in 1969. Right inside the ergosphere, a particle can have negative energy relative to an observer at infinity. This is a property of the rotating spacetime geometry, a consequence of how the Kerr metric defines energy in this region. If a particle enters the ergosphere and splits into two fragments, one fragment with negative energy falling into the event horizon, and one fragment with positive energy escaping back out, the escaping fragment can carry away more energy than the original particle brought in. The difference comes from the rotational energy of the black hole itself. The black hole loses a tiny amount of rotational energy, slows down by an infinitesimal amount, and the escaping fragment gains that energy. This is the Penrose process, and it means that a rotating black hole is not merely an object that traps energy. It is an object from which rotational energy can be extracted. Theoretically, up to 29% of the total mass energy of a maximally rotating black hole could be extracted this way. The Penrose process has never been directly observed in the form Penrose described it. But a related process, the Blandford-Zanajek mechanism, in which electromagnetic fields extract rotational energy from a Kerr black hole, is believed to be the power source for the relativistic jets that some black holes produce. The jets emerging from M87 and from many other active galactic nuclei, streams of plasma accelerated to near the speed of light and extending for hundreds of thousands of light years, may be powered by the rotational energy of the Kerr black hole at their source. The second profound difference between a Schwarzschild and a Kerr black hole is the geometry of the singularity. In a Schwarzschild black hole, the singularity is a point. All the mass is compressed to infinite density at a single location in space, a zero-dimensional point at the center of the black hole. In a Kerr black hole, the rotation prevents collapse to a point. The singularity is instead a ring, a one-dimensional circle of zero width and infinite density in the equatorial plane of the rotating black hole. This ring singularity has a property that the Schwarzschild point singularity does not. In principle, if you could survive the journey, you could pass through the center of a Kerr black hole without hitting the singularity. Now you would pass through the middle of the ring, through the zero of the ring, and emerge into a region of space-time with very strange properties. The mathematical solutions suggest this region may connect to another universe or another region of the same universe, though the physical reality of these inner regions is deeply uncertain and may be destroyed by quantum effects. Real black holes are almost certainly Kerr black holes. The no-hair theorem, one of the most elegant results in classical general relativity, states that a stationary black hole is completely described by just three parameters: mass, spin, and electric charge. Black holes in astrophysical settings are expected to have negligible net electric charge, because any charged black hole would quickly attract opposite charges from its environment and neutralize it, which means that real astrophysical black holes are described by just two parameters: mass and spin, and the spin is almost certainly non-zero. In 2025, a team of astronomers using artificial intelligence to analyze over 12 million simulations of the spacetime around Sagittarius A star confirmed that the Milky Way's central black hole is spinning at close to the maximum possible rate. The analysis used observations from multiple telescopes to constrain the spin parameter, and the result was unambiguous. Sagittarius A star is a rapidly rotating Kerr black hole. Its ergosphere is real. Its frame dragging is ongoing. The spacetime in the immediate vicinity of our galaxy's central black hole is being swept around in the direction of its rotation at a rate approaching the speed of light. CM 87 star, the first black hole to be imaged, has also been measured as spinning. The measurement of black hole spin is an active area of research. Spin affects the innermost stable circular orbit, the closest orbit at which material can stably circle a black hole before spiraling in. It affects the shape of the X-ray spectrum produced by material in the accretion disk. It affects the properties of the gravitational waves produced when two black holes merge. Gravitational wave observations from LIGO and Virgo have provided spin measurements for dozens of merging black holes. The distribution of spin values among these objects and the relationship between the spins of the two black holes in a merging pair is revealing information about how black holes form and how they pair up before merging. So the Kerr solution is not merely a more realistic description of a black hole. It is a description of a fundamentally different object than the Schwarzschild case, an object that drags spacetime, that has an ergosphere from which energy can be extracted, that has a ring singularity rather than a point, that carries angular momentum as a fundamental property, as fundamental as its mass. Almost every black hole we have detected is a Kerr black hole. The Schwarzschild black hole is a useful idealization, a mathematical tool. But the universe, with its universal rotation, its conserved angular momenta, its spinning stars and spiraling accretion disks, almost never produces the thing Schwarzschild's mathematics described. It produces Kerr black holes, rotating, dragging spacetime on extractable energy stored in the ergosphere, potentially driving the most powerful jets in the universe. And the most extreme members of this rotating class, the black holes that have been kicked from their host systems and now race through the universe unseen, are the subject of the next chapter. Most black holes stay where they are. A stellar black hole, formed from a dying star, remains in roughly the same region of the galaxy where the star lived and died. A supermassive black hole sits at the center of its host galaxy, where the density of matter is highest, where the conditions for accretion are most favorable, where the gravitational potential well is deepest. Most black holes have no reason to move, but some do, and some are moving right now, accelerated to velocities of millions of kilometers per hour, racing through the universe in directions that take them away from the galaxies that formed them, leaving no obvious trace of their passage. Invisible, undetected, detectable only in rare circumstances when they pass close enough to visible material to reveal themselves by the violence of the interaction. These are rogue black holes, and understanding how they form requires understanding one of the most counterintuitive results in gravitational physics. When two black holes merge, the merger is not symmetric. As two black holes spiral toward each other, losing energy to gravitational radiation, they emit gravitational waves asymmetrically. The waves are not emitted equally in all directions. Depending on the masses of the two black holes, their spins, and the orientation of their spins relative to their orbital plane, the gravitational wave emission is stronger in some directions than others. By Newton's third law, action equals reaction, this asymmetric emission of gravitational radiation imparts a recoil to the merged black hole, a kick. The merged object receives a velocity in a direction opposite to the dominant direction of gravitational wave emission. For certain combinations of mass ratio and spin orientation, this kick can be enormous. Theoretical calculations suggest that under specific conditions of near-equal mass ratio and anti-aligned spins, the gravitational recoil velocity can reach several thousand kilometers per second. The escape velocity from the center of a large galaxy is typically several hundred to around 1,000 kilometers per second, which means that in certain merger configurations, the kick imparted by gravitational recoil exceeds the escape velocity of the host galaxy. The merged black hole is ejected, thrown out of its galaxy at a velocity it cannot escape, and it leaves. The galaxy that assembled its progenitors over billions of years, the accretion of gas and dust and mergers with smaller galaxies that built the supermassive black holes whose merger created this recoil, cannot hold on to the product. The black hole departs, accelerating through space, heading somewhere. In 2023, astronomers announced the first confirmed observation of a runaway supermassive black hole in the act of leaving its galaxy. The object, found in a survey image from the Hubble Space Telescope, revealed itself not directly, but through a remarkable signature. What extending ahead of a galaxy in the image was a narrow, bright streak, a linear feature 200,000 light-years long. A wake, not of destroyed material, but of created material, of newly formed stars. As the runaway supermassive black hole had moved through the gas halo surrounding its host galaxy, its gravitational influence had compressed the gas it passed through, triggering star formation along its path. The black hole was leaving behind a trail of newly born stars, a line of infant star clusters marking its trajectory through the intergalactic medium. The black hole at the head of this stellar trail was estimated to have a mass of around 20 million solar masses. It was moving at approximately 1,600 kilometers per second relative to its host galaxy, fast enough to escape, fast enough to never return. In 2025, the James Webb Space Telescope confirmed a second runaway supermassive black hole, this one moving at 2.2 million miles per hour. Its trail, the wake of star formation it had triggered, provided a directional indicator. Its velocity vector traced back to its origin galaxy and forward to wherever it is currently heading. Two confirmed runaway supermassive black holes in the space of 2 years, after decades in which the phenomenon was theoretically expected but observationally unconfirmed. These are the dramatic cases. The rogue black holes announcing themselves through the scale of their passage, supermassive objects whose gravitational influence on interstellar gas is impossible to hide. But there is a more common and more silent category of rogue black hole. Dormant stellar black holes. Was a stellar black hole forming from a massive star's collapse receives a natal kick, an asymmetric push from the explosion itself. The supernova explosion is not perfectly symmetric. Material is ejected unevenly. The remnant, whether it becomes a neutron star or a black hole, receives a recoil from this asymmetric ejection. For neutron stars, natal kicks have been measured directly. Pulsars, rapidly rotating neutron stars, have been observed with transverse velocities of hundreds to over 1,000 kilometers per second, velocities that can only be explained by the natal kicks from their formation events. Black holes formed from the same process should receive similar kicks, though the asymmetry and therefore the kick velocity may be different depending on the mass of the progenitor and how much of the envelope falls back. The implication is that many stellar black holes in the Milky Way are not calmly orbiting the galactic center in the orbits their progenitor stars occupied. They have been kicked, sent on altered trajectories, some carrying them to the far reaches of the galactic halo, some escaping the Milky Way entirely if the kick was sufficient. The discovery of Gaia BH1 in 2022, the dormant stellar black hole just 1,560 light-years away, suggested something important. This object was not actively feeding. It had no accretion disk. It was detectable only because of the gravitational wobble it induced in its companion star. How many dormant stellar rogue black holes exist in the Milky Way, moving through the galaxy on altered trajectories from their natal kicks, invisible without a companion star to betray them, is unknown. The estimate of 100 million stellar black holes in the Milky Way is almost certainly dominated by dormant objects rather than the active X-ray binaries we have traditionally detected. The rogues are the majority, and occasionally, one of them passes through a region of sufficient gas density to briefly activate. In 2025, astronomers discovered an event they nicknamed Space Jaws. A black hole was observed in the act of tearing apart a star, in a process called a tidal disruption event, at a location 2,600 light-years from the center of a galaxy. This is not where supermassive black holes live. This is not where the stellar black holes typically associated with tidal disruption events of this magnitude reside. It was a wandering black hole, somewhere between stellar and intermediate mass, that had drifted to an unusual location and happened to encounter a star in a region far from any galaxy center. The star's material was stretched into streams by the tidal forces as it spiraled toward the black hole, heating to millions of degrees, briefly illuminating the location of an otherwise invisible rogue object. The universe is full of wandering black holes. Some of them are the product of supermassive mergers, kicked from galaxy centers with enough velocity to escape into the intergalactic void. Some are stellar remnants sent on altered trajectories by asymmetric supernova kicks. So some are the stripped remnants of smaller galaxies absorbed by larger ones, their central black holes no longer anchored to a galactic nucleus, but now drifting through the halo of the host galaxy. How often do rogue black holes pass through planetary systems? The probability for any individual solar system is extraordinarily small on any human timescale. The Milky Way is large, and the number of rogue black holes, while possibly large in absolute terms, is small compared to the volume of the galaxy. But over geological timescales, billions of years, the probability of a close encounter with a rogue stellar black hole is not negligible in the strict mathematical sense. The effect of such an encounter would depend entirely on the distance. A black hole passing at light-year distances would have no detectable effect on the solar system. One passing at the distance of a light week could perturb the Oort cloud, the distant reservoir of comets, and trigger an enhanced rate of cometary impacts on the inner planets over subsequent thousands of years. A truly close approach, at the scale of astronomical units, would be gravitationally catastrophic. But such an event is unlikely on any human timescale. Unlikely, not impossible. And the rogue black holes are out there, in numbers we have not counted, moving through space on trajectories we have not mapped, each one a dark gravity well, invisible, patient, occasionally announcing its location by the brief catastrophic flare of a star being torn apart. The most massive rogues, the ultramassive black holes at the extreme end of the mass spectrum, raise these stakes to a completely different level, on objects so massive that their gravitational influence extends for enormous distances. Objects whose event horizons alone are larger than our solar system. Those objects, and the question of how the universe produced anything so extreme, are next. The word supermassive was coined to describe something so far beyond ordinary stellar masses that a new word seemed necessary. A black hole containing 1 million solar masses. 10 million. 1 billion. Language straining against the scale. But the universe does not stop at 1 billion solar masses, and for the objects at the true upper end of the black hole mass spectrum, the objects that contain tens of billions of solar masses, the word supermassive is no longer adequate. These are ultramassive black holes. The boundary between supermassive and ultramassive is not universally defined. Different researchers place it at different thresholds, but a common convention places objects above roughly 10 billion solar masses in a distinct category, not merely large, supermassive black holes, objects that exist at a qualitatively different scale, whose properties depart from those of typical galactic nuclei in ways that require specific explanation. Consider TON 618. TON 618 is a quasar, an active galactic nucleus located approximately 10.5 billion light-years from Earth. The light we observe from it departed before our solar system existed. At its center is a black hole with a measured mass of 66 billion solar masses. 66 billion. The entire Milky Way contains perhaps a few hundred billion stars, with a total stellar mass of perhaps 50 to 60 billion solar masses. TON 618's central black hole alone contains more mass than the combined mass of all the stars in our galaxy. Its Schwarzschild radius, the radius of its event horizon, is approximately 1,300 times the distance between Earth and the Sun. An event horizon 1,300 astronomical units in diameter. The orbit of Pluto around the Sun has a radius of roughly 40 astronomical units. The event horizon of TON 618 extends more than 30 times the radius of Pluto's orbit. A spacecraft traveling at the speed of light would take weeks to cross it. Now consider what this means for an observer falling in. One of the most counterintuitive features of ultramassive black holes is that the tidal forces at their event horizons are extraordinarily weak. The tidal force at the event horizon of a black hole is inversely proportional to the square of its mass. For a black hole of 10 solar masses, the tidal forces at the event horizon would shred a human body millions of kilometers from the boundary. For a black hole of 66 billion solar masses, the tidal forces at the event horizon would be comparable to the tidal forces you experience on Earth's surface. Negligible. An observer falling into TON 618 would cross the event horizon without feeling anything unusual. No warning. No physical sensation marking the transition from the universe to the interior. The point of no return would pass undetected. And only later, as the observer continued inward toward the singularity at the center, would the tidal forces become significant. This is perhaps the strangest implication of general relativity applied to ultramassive black holes. The more massive the black hole, the less violent the experience of crossing its event horizon. A black hole massive enough makes the event horizon, the most extreme boundary in the known universe, essentially invisible to an infalling observer. The density paradox is equally striking. Average density, defined as mass divided by the volume enclosed within the event horizon, decreases as a black hole's mass increases. For a black hole of 10 solar masses, the average density within the event horizon is millions of times the density of atomic nuclei. Extraordinarily dense. For TON 618, with its 66 billion solar mass event horizon, the average density within the event horizon is less than the density of water. An ultramassive black hole is, on average, less dense than water. Not because it is loosely packed. The singularity at its center is infinitely dense in the classical description, but because its event horizon is so large that the volume it encloses is enormous relative to the mass contained within it. Phoenix A is the leading candidate for the most massive known black hole. Located at the center of the Phoenix cluster, a massive galaxy cluster roughly 5.8 billion light-years from Earth. Phoenix A has an estimated mass of 100 billion solar masses. 100 billion. At this scale, numbers lose their intuitive meaning, but one comparison conveys something of what it represents. If you replaced the Sun with Phoenix A, its event horizon would extend roughly 4,500 astronomical units from its center. The nearest star to our Sun, Proxima Centauri, is approximately 268,000 astronomical units away. Phoenix A's event horizon would not reach even a fraction of the distance to the nearest other star. And yet, it is already larger than the entire solar system by an enormous margin. In 2025, a new competitor for the most massive known black hole was announced. A team using the Dark Energy Spectroscopic Instrument and data from strong gravitational lensing identified a black hole located approximately 5 billion light-years from Earth, at the center of one of the most massive known galaxies, with an estimated mass of 36 billion solar masses. Below Phoenix A's estimate, but within the same extraordinary category, and crucially, the method used to estimate its mass, gravitational lensing, is independent of the assumptions that carry larger uncertainties in the Phoenix A estimate. The cosmic Himalayas discovery of 2025 added another dimension to the ultramassive picture. An international team using the Subaru telescope identified the most extreme concentration of active supermassive black holes ever found, a cluster of quasars tightly packed together at a look-back time of 10.8 billion years, existing when the universe was roughly 3 billion years old. The discovery team named it the Cosmic Himalayas because the density of active black holes stood out from the surrounding universe like a mountain range above a flat plain. The objects in the cosmic Himalayas are not yet ultramassive by current estimates, but their extreme concentration and apparent coordinated activity raises questions about whether some environments in the early universe provided conditions for exceptional black hole growth. Whether the clustering itself accelerates the growth of individual members through enhanced merger rates or enhanced accretion of the same dense gas supply. The formation of ultramassive black holes is genuinely mysterious. Standard accretion models, even with maximum accretion rates, struggle to build objects of 60 to 100 billion solar masses in the available cosmic time. The most massive ultramassive black holes are found in the most massive galaxies, which are themselves found at the centers of the most massive galaxy clusters. The environment matters. The leading hypotheses involve combinations of factors. Multiple mergers of already massive supermassive black holes. When galaxy clusters merge, their central black holes eventually merge as well, creating a more massive combined object. Now, if a galaxy cluster has undergone many major mergers over cosmic time, building the most massive cluster in the observable universe, its central black hole may have undergone many mergers of its own. Super-Eddington accretion in the early universe. Accretion rates that theoretically exceed the limit imposed by radiation pressure. Possible in environments where the accreting gas is dense and opaque enough to suppress the outward radiation. If ultramassive black holes accreted at super-Eddington rates during phases of abundant gas supply in the early universe, they could have reached extraordinary masses before the current epoch. And primordial seeds. Massive black holes formed directly in the early universe before normal stellar evolution began, that had billions of years of additional accretion to accumulate further mass. But perhaps all three contributed. Perhaps different ultramassive black holes followed different paths to their current scales. What is certain is that they exist. TON 618 is not a theoretical construct. It is a measured, observed, imaged object. Phoenix A is inferred, but its environment, one of the most massive galaxy clusters known, supports its extreme estimated mass. The universe made these objects, built them over billions of years through processes we are still working to understand, and they sit at the centers of the most massive galaxies, shaping the large-scale structure of the universe around them through their gravitational influence and their occasional episodes of energetic feedback, each one a gravitational anchor for a structure of matter that extends for tens of millions of light-years in every direction. The largest, the most extreme, and yet, for all their size, completely describable by the same three numbers that describe the smallest stellar black hole: mass, spin, charge. The no-hair theorem does not know the difference between a stellar black hole of 10 solar masses and an ultramassive one of 100 billion. It sees only those three quantities. And this brings us to the final chapter, and perhaps the strangest territory in all of black hole physics: the smallest possible black holes. Objects so tiny that quantum mechanics becomes dominant, where the deterministic geometry of general relativity gives way to probabilities and uncertainties, where black holes do not merely consume but gradually evaporate, and where the deepest unresolved tension in all of physics lives. That territory, the micro-black hole, is next. Stephen Hawking was 29 years old in 1965. He had recently received his diagnosis of motor neuron disease. He had recently married. He had recently committed, with characteristic stubbornness, to building a career in theoretical physics, despite everything his prognosis implied about the future. And he had recently begun thinking seriously about the quantum mechanics of black holes. General relativity, Einstein's theory, describes black holes as perfectly stable objects. Once formed, they persist. Their event horizons are immutable. Nothing escapes. The information that falls in is gone. The mass is locked away forever. Quantum mechanics describes a universe pervaded by fluctuations. Empty space is not truly empty. It is filled with the constant creation and annihilation of virtual particle pairs, particles and antiparticles that flash into existence and immediately annihilate each other, borrowing energy from the quantum vacuum for intervals so brief that the uncertainty principle permits it. These two pictures, general relativity and quantum mechanics, are the two most successful theories in the history of physics. Each is extraordinarily well tested in its own domain. Each makes predictions verified to extraordinary precision, and they disagree with each other in the vicinity of a black hole. In 1974, Hawking published a paper that attempted to resolve this disagreement, and in doing so predicted one of the most elegant and disturbing results in all of theoretical physics. But black holes are not perfectly stable. They radiate. The mechanism Hawking described works as follows. Virtual particle pairs are constantly being created just outside the event horizon of a black hole, as they are everywhere in space. Normally, these pairs annihilate immediately. But in the presence of the extreme space-time curvature near an event horizon, the fate of the two particles can be separated. One particle falls through the event horizon into the black hole. The other escapes to infinity. The escaping particle carries positive energy. The infalling particle carries negative energy, relative to an observer at infinity, which is permitted by the space-time geometry of the region just outside the event horizon. The net effect is that the black hole has emitted a particle. And because the infalling negative energy particle reduces the black hole's total mass energy, the black hole has lost mass in the process. The black hole is shrinking, radiating energy, evaporating. The temperature of this radiation, now called Hawking radiation, is inversely proportional to the mass of the black hole. Larger black holes radiate at lower temperatures. Smaller black holes radiate at higher temperatures. For Sagittarius A star, with its 4 million solar masses, the Hawking temperature is approximately 10 to the power of -14 Kelvin. This is 14 orders of magnitude colder than the cosmic microwave background. The residual thermal radiation left over from the Big Bang that permeates all of space at a temperature of approximately 2.7 Kelvin. The cosmic microwave background is delivering far more energy to Sagittarius A star than Sagittarius A star is radiating away. It is effectively gaining mass faster than Hawking radiation can remove it. For a stellar black hole of 10 solar masses, the Hawking temperature is even lower, even colder than Sagittarius A star. For a primordial black hole with the mass of a mountain, the Hawking temperature rises to detectable levels, and for a black hole with the mass of a large asteroid. The Hawking temperature is hot enough that the object is radiating X-rays and gamma rays at a significant rate and evaporating on cosmological timescales. For a micro black hole, an object with the mass of a few kilograms or less, the Hawking temperature is so high that it would evaporate almost instantly. A black hole with the mass of a human being would evaporate in a tiny fraction of a second in a burst of gamma radiation. This is why the Large Hadron Collider at CERN, despite the fears expressed by some members of the public when it began operations, posed absolutely no danger from micro black holes. The LHC produces collisions at energies high enough that quantum gravity effects might theoretically allow the creation of micro black holes, objects with masses at the Planck scale, roughly 10 to the power of -5 grams, the scale at which quantum gravitational effects become important. These objects, if they formed at all, would have Hawking temperatures of around 10 to the power of 32 Kelvin, unimaginably hot, and would evaporate in approximately 10 to the power of -43 seconds. With a time interval so brief it is smaller than the Planck time, the smallest meaningful time interval in physics. No detector on Earth could observe such an event. The black hole would exist for a shorter time than it takes light to cross the diameter of a proton. The LHC has found no evidence of micro black hole production. This null result is itself informative. It places constraints on theories of extra dimensions and quantum gravity that predicted such production would occur. The information paradox is the deepest problem Hawking radiation creates. According to quantum mechanics, information cannot be destroyed. This is a fundamental principle called unitarity. Any quantum system evolves in a way that preserves information. Given the current state of a system, its past state can in principle be reconstructed. But if a black hole evaporates completely through Hawking radiation, what happens to the information that fell in? Hawking's original calculation suggests that Hawking radiation is purely thermal, that it carries no information about what fell into the black hole. It is like the heat from a furnace. It tells you something was burned, but not what the original fuel was. If this is correct, and the black hole eventually evaporates completely, the information is gone. The past state cannot be reconstructed from the radiation. Unitarity is violated. This is the black hole information paradox. It has occupied theoretical physicists for 50 years. The resolution has not been found, but progress has been made. In 2019, a series of papers by Pennington and independently by Almheri, Mahajan, Maldacena, On and Zhao introduced a new approach using a concept called the island formula. In this framework, at late times in the evaporation of a black hole, a region called the island forms inside the black hole. Calculating the entanglement entropy of the Hawking radiation using the island formula gives a result consistent with unitarity. The entropy rises and then falls following what is called the Page curve. This suggests that information is not lost, that Hawking radiation does carry information about what fell in, though in a form so scrambled and complex that recovering it would require quantum operations of extraordinary sophistication. The information paradox may be on the way to resolution, yes, but the resolution requires, or at least strongly suggests, that the interior of a black hole and the exterior radiation field are connected in ways that general relativity alone cannot describe. That the correct theory of quantum gravity, still unknown, would reveal a deep entanglement between the Hawking radiation and the interior of the black hole. In 2025, new calculations revise the timescale on which the universe decays through quantum processes, including Hawking-like radiation from other objects. The last stellar remnants, neutron stars and white dwarfs, were previously estimated to evaporate through Hawking-like radiation on timescales of roughly 10 to the power of 1,000 years. The new calculations brought this estimate dramatically downward to approximately 10 to the power of 78 years, and still an unimaginably large number, still more than 10 billion times the current age of the universe, but significantly shorter than previous estimates. The universe is decaying faster than we thought. And at the very end of that process, in the era when the last stellar remnants have evaporated, the only remaining macroscopic objects will be the black holes themselves. The stellar black holes will take longer to evaporate than their stellar counterparts, but they too will eventually go. Their Hawking temperature will rise as their mass decreases, the evaporation will accelerate, and in their final moments, in a burst of gamma radiation lasting a fraction of a second, they will vanish. After a time incomprehensible in human terms, the supermassive black holes will follow, and then the ultramassive ones, each one's evaporation taking longer than the one before. The very last object in the universe, the last thing to survive, will be the most massive black hole. And when it evaporates, in a final burst of radiation, the universe will be empty. No matter, no energy except the residual thermal radiation expanding forever, a cold, dark, uniform void. This is the end of the black hole era. And the fact that we know this, that we can calculate when it will happen, what the temperature of the final Hawking burst will be, how long the last black hole will survive, is one of the most extraordinary things about physics. We understand these objects well enough to predict their deaths, even the deaths of objects that will outlive every star, every planet, every structure the universe will ever build. And that understanding, imperfect, incomplete, contested in its details, is what 8 chapters of this documentary have been building toward, not just a taxonomy of black hole types, but an understanding of what each type reveals about the universe. The stellar black hole reveals the end of stars and the silence of the majority. The intermediate black hole reveals the missing link between stellar evolution and galactic structure. The supermassive black hole reveals the co-evolution of galaxies and the monsters at their centers. The primordial black hole raises the possibility that dark matter was made in the first second of time. The Kerr black hole reveals that rotation is fundamental, that space-time itself can be dragged, that energy can be extracted from the vacuum of space-time itself. The rogue black hole reveals that these objects move, that they are kicked and scattered and sent racing through the universe on trajectories that carry them away from their origins. The ultramassive black hole reveals the ultimate scale that gravity achieves, and asks how the universe built something so extreme, and the micro-black hole, and Hawking radiation reveals that black holes are not eternal. That even the most extreme objects in the universe obey the laws of quantum mechanics. That information, perhaps, is preserved. That the universe ends not with infinite persistence, but with a slow, quiet evaporation that takes longer than any human timescale, but is finite nonetheless. 8 types, 1 object. Or rather, 1 name shared by 8 profoundly different things. All of them extreme. All of them real. Yes, all of them teaching us something that cannot be learned any other way. And all of them out there right now, in the dark, in the silence, doing what black holes do. Let everything go quiet now. The science is done. The 8 types have been named and measured and placed in their contexts. The universe has been described, as far as we can describe it, from the smallest possible black hole to the largest. And somewhere out there, at every scale we discuss tonight, they persist. The dormant stellar black holes. 100 million of them in our galaxy alone. Most invisible, most silent, orbiting the galactic center in the dark, waiting to be found by a spacecraft patient enough to watch the stars they perturb. The intermediate black holes in the cores of globular clusters, the missing links, confirmed at last, sitting at the centers of ancient spheres of stars that have been orbiting the Milky Way since before the solar system formed. Sagittarius A star, 26,000 light-years away, 4 million solar masses, its space tornadoes turning in the dark at the center of our galaxy, spinning at near maximum rate. Quiet for now. The primordial black holes, if they exist, drifting through the universe since the first second of time, invisible, possibly constituting the dark matter that holds every galaxy together. TON 618, 66 billion solar masses, its light taking 10 billion years to reach us, already ancient when the sun ignited. So massive that its event horizon is larger than our solar system. The runaway supermassive black hole, racing through intergalactic space at 2.2 million miles per hour, its trail of newly born stars the only evidence of its passage. And somewhere, in the final moments of the universe's life, a micro black hole radiating its last, a final burst of gamma rays, a flash, and then nothing. Let your body be still. You do not need to hold any of this tonight. The black holes will continue without your attention. Their orbits do not require witnesses. Their accretion disks do not require observation to turn. Their Hawking radiation does not require detection to occur. They simply are, as they have been, for timescales that make the age of the universe seem like a brief introduction. Let your breath slow. Let your thoughts drift outward past the sun, past the 8 planets, into the scattered disk where Gong Gong orbits its ancient red loop, past the heliopause where the solar wind meets the interstellar medium, and into the dark between the stars, into the Milky Way's vast disk of hundreds of billions of suns, with its 100 million invisible black holes orbiting quietly among them, into the galactic center where Sagittarius A star turns in silence, and outward still, past the Andromeda galaxy, past the local group, past the Virgo supercluster, into the deep universe where quasars burned when the cosmos was young, where ultramassive black holes grew to scales the human mind was not built to contain. The universe contains all of this simultaneously, at this moment. While you rest, it does not slow down for sleep. It does not pause for human attention. The black holes are turning and accreting, and occasionally flaring, and slowly evaporating exactly as they always have, on timescales that make every human life an imperceptibly brief event. And that, if you let it, is a restful thought. You are not responsible for any of this. You did not make it. You cannot change it. You can only, occasionally, understand a little more of it. And tonight, you understood a little more. 8 types. 1 name. Infinite darkness. Good night.